Good morning, everyone. Today, we will explore the structured approach to servo system steady-state control planning, a key process in motion control that ensures precise, stable, and disturbance-resistant performance once a system reaches equilibrium. While dynamic response focuses on rapid motion changes, steady-state control maintains accuracy and stability during continuous operation, which is essential in high-precision fields like robotics, CNC machining, and automation. Our planning framework consists of 5 systematic steps: defining clear performance indicators, designing the controller structure, tuning parameters, integrating disturbance rejection strategies, and finally implementing and verifying the system. This structured methodology helps engineers address real-world challenges such as mechanical resonance, sensor noise, and thermal effects early in the design phase, ensuring robust and reliable servo performance in practical applications. The first and most critical step is to define clear, quantifiable performance indicators. These indicators serve as the design goals and evaluation criteria for the entire control system. The primary metrics include tracking accuracy, which refers to the allowable steady-state error under constant or slowly varying commands. For example, in a positioning system, this might be specified as +1 pulse or ±0.01 degrees. Next, we consider disturbance rejection, which measures the system's ability to recover from external disturbances such as load changes or friction variations. This is often expressed in terms of recovery speed and maximum deviation. Finally, stability is non-negotiable. The system must remain absolutely stable during steady-state operation. Typically, we aim for a phase margin greater than 45 degrees and a gain margin exceeding 6 dB. These indicators guide all subsequent design decisions and ensure that the control system meets real-world performance requirements. Once the performance indicators are set, we move on to designing the controller structure and selecting the right algorithms. This step is the core of achieving our performance goals. We typically employ a layered control strategy, starting with the innermost torque or current loop, which provides fast and precise torque output. This loop usually uses a high-bandwidth pi controller. For the outer position and velocity loops, we often rely on classical PID control and its variants. The proportional term P determines system stiffness, the integral term I eliminates steady-state error, and the derivative term D improves stability and suppresses overshoot. Additionally, we may incorporate feed-forward control, such as velocity and acceleration feed-forward, to reduce tracking lag and improve dynamic accuracy. For more complex systems, advanced algorithms like sliding mode control or adaptive control can be considered. We also integrate enhancement modules like disturbance observers DOB and resonance suppressors to improve robustness and prevent mechanical oscillations. With the controller structure in place, the next step is systematic parameter tuning. This process must be carried out in a specific order. First, tune the innermost current loop, then the velocity loop, and finally the position loop. We always start with simulation tools like MATLAB Simulink to perform frequency domain and time domain analyses. This allows us to evaluate stability margins, step responses, and disturbance rejection capabilities in a risk-free environment. Once the simulation results are satisfactory, we proceed to on-site fine-tuning. A common tuning approach is to adjust P first until slight oscillation occurs, then reduce it slightly. Next, we introduce I to eliminate steady-state error, and finally, we add D to suppress overshoot. Throughout this process, we rely on both auditory and visual feedback, listening for smooth motor operation and observing response curves for signs of overshoot or oscillation. This iterative tuning process is essential for achieving optimal performance. A successful control plan must also address practical engineering challenges. One key consideration is measurement noise, which can come from encoders or current sensors and significantly impact steady-state accuracy. To mitigate this, we implement both hardware filtering, such as RC circuits, and software filtering, like moving average or low-pass filters. Another critical factor is mechanical resonance. The controller bandwidth must be carefully planned to avoid exciting the natural frequencies of the mechanical system, typically set below 1/3 of the resonant frequency. Additionally, long-term operation introduces challenges like thermal drift and nonlinearities due to motor heating and friction changes. To address these, we either design with sufficient margin or incorporate temperature compensation mechanisms. By considering these implementation details early in the planning phase, we ensure that the control system remains reliable and accurate under real-world conditions. In summary, steady-state control planning for servo systems is a systematic and layered engineering process. It begins with clear performance indicators, proceeds through structured controller design and parameter tuning, and culminates in a robust and reliable control system. Success depends not only on a solid understanding of control theory, but also on practical insights into the physical system, including motor characteristics, load dynamics, and environmental factors. For your own projects, I recommend applying this framework while carefully considering the specific parameters of your chosen motor, such as torque constant, back EMF constant, and rotor inertia. Additionally, always validate your design through simulation before moving to on-site implementation. With careful planning and iterative refinement, you can develop servo systems that deliver exceptional steady-state performance in even the most demanding applications. This is the end of today's training. Thank you for your listening.